So I'm going to give a rather contrarian talk at the seminar, and I'm going to tell you about some models that are not low rank and why they're better. Okay, but there's some secret low rank that comes in at the end. Okay, so don't be too upset. This is based on so I'm going to show you how to impute missing data, not using low rank models, but using the Gaussian Copula model. And this is based on joint work with my PhD student, Yixuan Zhao, who is awesome, and two fantastic undergraduates at Cornell, Eric and Elliot. Okay, so the motivation is imputing missing data in large-scale data tables. So here's an example of the kind of data table I have in mind. It's a survey data set. Here I've got every row is a person, okay? So I know some things about the people. Maybe I know how old they are. Maybe I know what gender they have recorded on this form. Maybe I know what state they're in or what their income is or their level of education, okay? And the things to observe about this data set are, well, I'm showing 4 rows, but there could be a lot of rows. I'm showing, 5 columns, but there could be lots of columns. And the most important thing to observe is that the values are not necessarily continuous. Okay, I've got income, which, well, it's positive, hopefully, almost always positive. Okay, and it has a weird distribution, right? If you try to fit income with like a squared error loss, you're going to be in big trouble because it's heavy-tailed, right? And you're going to end up overfitting to the billionaires. Okay. Now, look at something like education, and this is ordinal, okay? Like a high school education is less than a master's degree, is less than a college education, is less than a master's degree, is less than a PhD. By how much, I don't know, right? Can we ask questions like, is a high school education more different from a master's degree than college is from a PhD? Right? How would we think about that question? Okay, and then most importantly, there are these missing values. Okay, so we want to impute the missing values, and they should be imputed with values that are from the appropriate distribution. So I want the imputations in income to look like incomes, so they shouldn't be like wildly negative. They shouldn't be, I shouldn't be imputing most of them to be millionaires because they're not, right? The imputations in education should be ordinals, etc. Okay. So our goals are things like to impute missing entries, maybe to generate confidence values for these imputations. Which ones am I right about? And when am I confidently right about? And which ones really can I not say? Can I quantify the impact of imputation on downstream analyses? And can I identify related features, right? Which of these features tend to covary and which ones don't, right? These are kind of interesting questions just to be able to understand a data set like this. Okay, so more generally, I'm going to imagine that I've got a data table, which I'm going to call X. It has n rows. These are examples, so something like patients in a hospital, respondents on a survey, assets in a financial model. And it has P features. These are the columns. These might be things like tests that I've given to these patients, questions answered by the respondents on a survey, performance indicators for these assets. Okay. So the notation I'm going to use is that X upper I is the ith row of X. That's the feature vector for the ith example. Notice that the entries of X upper I might have different types. Okay, and X sub j, that's the values of the jth feature across all the examples. All of those things have the same type. Okay, great. So the classic approach to this problem, I would say, is low-rank matrix completion. And I'm a big fan of low-rank matrix completion. I've done a lot of stuff on low-rank matrix completion. Many people here have as well, right? And why do we like it, right? They're efficient algorithms. They come with theoretical guarantees. It works really well when the true rank is small compared to the minimum of the side lengths of this matrix. And it works also well when the true rank is just the true matrix is approximately low rank. Okay. On the other hand, it works pretty poorly for ordinal data or for mixed data, where some of the columns are ordinal or binary in addition to continuous. The reason is that it requires additional parameters, like a loss function, to tell you, how to measure how to measure errors between the imputed values and the true values. Even for real values, this can be a huge problem, as you saw with the income field, right? How should I measure errors on income? Like clearly, large errors on large incomes are less important than large errors on small incomes. By how much? How do I quantify this? So that introduces a lot of extra parameters to map from some latent low rank thing to the observations that we have, which might be binary, which might be ordinal, okay, which might be continuous with some weird distribution. Okay, so how do you handle this in a low rank model? Oftentimes people do it by choosing loss functions. But if you choose a loss function for every different column, that's a huge number of extra hyperparameters that you have to choose. So if you're picking these by cross-validation, right, then you're fitting a lot of models. And even if your method for fitting low-rank models is really fast, your overall routine is really slow because you've got a lot of hyperparameters cross-validate over these losses. And you've got the rank, which is an important hyperparameter to prevent overfitting in a low-rank model. Okay. Once again, let's remember why we think, why did we think that data matrices were often approximately low rank? And part of the reason is that sort of squarish matrices should be low rank. Essentially, the reason for this, right, the reason why you need a matrix to be squarish to be approximately low rank is that the column rank is equal to the row rank, right? This is a fundamental fact of linear algebra. And so that means that the number of features that we're fitting for every row is equal to the number of features that we're fitting for every column. Okay, the number of degrees of freedom of our model is the same per row and per column. Okay, that's fundamental to low rank. Okay, if you have a long, skinny data matrix, then it's not a great idea to fit it using a low rank model. Okay, the reason is you have many more observations per column, right, for your long, skinny matrix than you have per row, right? So you should be fitting fewer parameters per row than per column. You can afford to fit something much more complex for the columns. Okay, great. So let's do it. Okay, so let's remark again, right? The imputation challenge really depends on the data. Depends on the size, whether there are few columns or many columns. Depends on the types, whether the value is continuous, ordinal, binary, categorical, or mixed. And it depends on how you have access to the data online. Maybe you have online or streaming access, or maybe you have sort of batch access to everything at once. Okay, our goals for imputation are high accuracy imputations, quantified uncertainty. So we're actually going to try to get confidence intervals for estimates, and estimations for the impact on downstream analyses. Once again, which you can do by confidence intervals, and understanding correlations between features. Okay. So to do all this stuff, I'd like to introduce you to the Gaussian Copula model. This is, in some sense, it's a really old school model. It's been around for a really long time. It was blamed for causing the financial collapse of 2008. But my claim is that was for mortgage-backed securities, okay, not for tabular survey data. So I think we're safe on tabular survey data. Okay, so let me tell you about this. So we say that data vector X, okay, so think about this like a row of our data table, follows the Gaussian Copula model with covariance sigma and marginals F, okay? If there exists a latent vector Z that's distributed like a normal random vector, mean 0, and correlation matrix sigma. Okay, so sorry, sigma is a correlation matrix, not a covariance matrix. Okay, so it's a special covariance matrix. It's a correlation matrix. The diagonal is the identity. And it has marginals, f of z. So what I mean by that is that every entry of x is given by, right, the jth entry of x is given by the jth function applied to the jth entry of z. Okay, so I've got this vector z that's a Gaussian random variable, right? So, its distribution looks like some ellipse, okay? You pick out, right, the Gaussian random variable, and then every entry of that gets mapped through some monotonic function to give you the value that you actually observed. Okay. Why would we model data using Copula? The first reason is that this models nonlinear rulers. What I mean by that is, imagine you really have, you have some data. Let's say, how loud is a sound? Okay. How do you measure how loud is a sound? Okay, well, you could measure it in terms of the displacement of someone's eardrum when they hear the sound. You could measure it in decibels. You could measure it in the absolute energy contained in that sound signal. You could measure it in someone's rating of how loud that sound is on a scale from 1 to 7. Okay, so all of these are examples of rulers, right, that we're using to measure sound, and they're going to generate really different measurements. So in particular, if we measured a bunch of sounds and had a bunch of people measure them, and we made a matrix of these sounds, whether or not that matrix is low rank is going to depend on what kind of ruler we use. Okay, the Gaussian Copula model explicitly models the ruler, right, this f, and so it gets rid of that nuisance parameter. Second thing I like about it is that it separates the interactions from the marginals. So once again, you get rid of the, the effect of this nonlinear ruler in F, and then the rest is put into this correlation. A third thing that you might like is the fact that it's, if you allowed the copula to be anything rather than a Gaussian distribution, you can fit any distribution using this model. Now the Gaussian distribution, that's very special. On the other hand, low rank models, probabilistic PCA in particular, assumes that the data itself is Gaussian. So I would say that modeling the data as Gaussian measured by a nonlinear ruler is at least more general. Okay. So here's an example of what that might look like. So imagine that your latent variable, z, is on this x-axis. Okay, so it takes on a normal value. Right, there's a normal distribution. And what I'm going to observe is on this axis. Okay, so this f function is telling me how to map the latent variable to the value that I observed. Here's an example that generates ordinal data. I map any latent value between -infinity and 1 to the value 1, anything between -1 and 1 to the value 2, and anything between 1 and infinity to the value 3. Okay. So if the observations that I made are continuous, then I'm going to see this function f is a continuous function. And in particular, it will be invertible. So that means from any x, I can figure out what the latent z was, and from any z, I can figure out what the observed f is. Okay. If if the observations are actually ordinal, then from any latent value, I can figure out, for say the value is 0, I can figure out what the observed value should be. But from any observed value, all I can do is figure out an interval in which the latent value lies. Okay, that's going to be important for estimation. Okay, so I'm going to write f inverse of an observed value x to represent that entire set, right? The set of, right, so if I observe value 2, the set of values z from which that 2 could have come is this whole interval -1 to 1. Okay, so f inverse is going to be an interval in general. Okay, so you'll observe that the marginals distort correlations. Okay, so imagine that I had, right, I really have some Gaussian data, z. Okay, so it's normally distributed, and then I pick some cutoffs. So I'm going to pick a cutoff here and value and for the first axis, and cutoffs here and here for the second dimension. And I'm going to imagine that I don't observe the original Gaussian data. Instead, I observe whether or not you are below the first cutoff, between the first 2 cutoffs, or above the second cutoff. Okay, so this generates data that looks like this. Here's the continuous first dimension. Here's the now discrete second dimension. And I can do this again, right, to generate the following, right? Here's the discrete first dimension. Here's the discrete second dimension. Okay, and you can see that I've turned all of my data, and now there are only 7 points represented. So of course, if I compute correlations between my data in this discrete space, I'm going to get something different than if I compute correlations between my data in the original space. In fact, I'm going to get that the correlation is lower. Okay, so you might ask, if I have discrete data presented to me, right, and I want to know the correlations between 2 features, does it make sense to do it in this space, or does it make more sense to try to figure out what the original data used to be, what this real Gaussian data is, and to compute correlations here? Now, I would argue that correlations are fundamentally a Gaussian thing, and so it doesn't make so much sense to compute correlations on discrete data. Okay. Great. Okay, so all that's motivation. There have been lots of people studying similar models. Many people have studied Gaussian copula models before, together with ways of estimating them. The closest work is this work by Peter Hoff which proposes a Markov chain Monte Carlo. The main contribution of our first paper on this was a faster approximate EM method to estimate the same model. And then we improved it to use a low rank covariance matrix, which I'll show you in the end of this talk, which allows you to fit it for extremely large data sets like movie lens. Okay. There have also been sort of people in the low rank approximation community who have explored sort of models motivated by similar things, where you're trying to understand the effect of nonlinear marginals. So Ravi Ganti, Rebecca Willett, and Laura Bolzano worked on this really nice model that sort of puts nonlinear marginals on top of a low rank model and estimates it. It's super cool work, and we were very inspired by it, but it also doesn't work very well for large scale data. And there's some weird problem where as you iterate it more, it actually converges to worse estimates. So essentially the reason for that is that you're doing sort of optimization, and the fundamental insight of this Gaussian Copula work compared to that model is that we're marginalizing over the latent value. And I have to tell you, like, I didn't believe this at first because I'm sort of an optimizer at heart. And my student kept coming back and saying, no, we have to marginalize. And Yusman was absolutely right. So it's pretty cool. Okay, and then the second work is called XPCA by Anderson Bergman and Temi Kolda. They were also motivated by a copula model, but they do something weird to it. They actually fit a low rank mean to the model, but assume a diagonal covariance, so it gets rid of the correlational structure, which is the most important thing about a copula. Okay. Okay, so our method, what does it do? It fits a copula model. It's fully probabilistic, so you get confidence intervals for the estimates. Has no hyperparameters except for computational efficiency. So there's no problem with overfitting. And you can fit it with this fast approximate EM method. Okay. So how does it work? So first, let me argue that given the parameters of the model, like if you knew the marginals and the copula, then imputation would be really easy with this model. Okay. So suppose I know the marginals in the copula, and I observe some set of entries, x obs, for a new row. So obs is going to be a subset of the indices of the columns. Okay, the missing entries are going to be the complement of that set. Okay, so I'm going to impute the missing entries by observing that the latent vector of missing values is normal, and we can actually compute its mean and variance. Okay, so given the observations, I use F inverse, which for continuous data is invertible, to compute the latent Gaussian entries corresponding to the observed variables. Okay. Next step is normality. Okay, so the latent missing variables are normal given the latent observed variables, and you can compute the mean and the variance. The variance is just the short complement. It's all very canonical. Okay. Now we can predict the missing values with their mean. We could also write down the confidence interval, right? We've got a full distributional understanding of what's going on. Okay, and then to map to the observed values, you just map them through the marginals F.
I think you have a question, Madeleine, in the chat. Like, do we need marginal density for each variable?
Yes, so you need to know the correct marginal F that corresponds to each variable. That's actually easy to estimate. The thing that's hard to estimate is the variance. But here I'm assuming that you know both of them.
So let me ask another question. I mean, if part of the motivation that you use is discrete values, I mean, somehow this assumption that you have that there is an F inverse.
That's just for this slide.
Oh, okay.
Yeah. Okay. So now let's go to the hard case, which is that there isn't an F inverse. Okay. So let's think about what this looks like. Okay. So over here on the right column, let's imagine this is so what I'm plotting is the PDFs of my data. Okay. So for continuous data, I've got a continuous PDF for the first variable, continuous PDF for the second variable. For discrete ordinal data, I have a discrete PDF. Okay. So there's a point mass on 3 values for a discrete variable with 3 values. Okay, for binary data, I've got 2 point masses. Okay, so let's imagine that this is what I observed. I observed the first variable. Okay, and I can figure out exactly what the latent value corresponding to that first variable is because this F is invertible because it's continuous. Okay. In fact, you can sort of view it by just you've enforced that the f is monotonic, so you can figure out which z corresponds to which f just by matching quantiles. Okay. Great. Second variable, I have not observed it. It's missing. Okay, so I have no idea what z it corresponds to. It could be anything in this interval. Third variable, I've observed that it has value 2, right, out of 3 possible values. So by what I can figure out that it's in sort of the middle third of the distribution of z values, but I don't know where. Okay. Fourth one, I've observed the top value of this binary variable, so I know it's in the right half of this distribution. Okay, and the middle one is missing. The last one is missing, so it could be anywhere in this interval. Okay, so in other words, I don't know what z is anymore. What I do know is it's constrained to a product of intervals.
So you're also assuming that the discrete variables, they have a linear order or something like this.
Yes. So they're all ordinal. So this is not so actually the one thing that we don't know how to do with this model is categorical variables. Yeah. So ordinal, Boolean, and real. Okay. So if I've got this, how do I impute missing entries? Okay. So now my f's are not invertible. Okay, I have the observed entries for a new row, x obs, and the missing entries of the complement. Okay. Once again, I'm going to impute the missing entries using the normality of the missing data. So if I knew z obs, right, if I had a point estimate for that, right, then I would still use normality, just like in the previous slide. Okay, but I don't. Okay, instead, what I'm going to do is take the expectation given x observed. Okay, so the expectation of the missing values given x observed, right, is the expectation of this mean given x observed, right? Luckily, this is linear in z observed, right? The rest of the stuff is right constant parameters of the model. Okay, so I get, so all I'm doing is I'm replacing z observed with its expectation given x observed. Okay, so it's pretty straightforward. And then I can map back to the observed space as before using the marginals. Okay, how do I estimate the parameters? And I'm going super slow. So I think I'm going to tell you this in a very hand-wavy way, and I would be very happy to explain it more later, but it's, you know, it's not too complicated. So there are 2 parameters to estimate, right? The marginals and the copula correlation. Okay. To estimate the marginals, we've already talked about how to do this. It's pretty straightforward. I'm just going to show you again on the picture. You just match quantiles. Okay, so the first, right, the first percentile of the data maps to the first percentile of the data of the Gaussian. Okay, so you can write down a mathematical form for that, and it looks like this. You take the inverse Gaussian CDF, and it gives you what you need. Great. Okay. How do you estimate the copula? This is actually, so for complete continuous data, this is really easy. Okay, you can estimate the copula using maximum likelihood estimation. First thing you do is you compute the latent Gaussian variable for every row. Okay, you write down the log likelihood, and you can see that it's maximized by the empirical correlation matrix. Okay, so this is the important fact. Maximized by the empirical correlation matrix of these Gaussian latent variables. Okay. Now that's a correlation, a covariance matrix. We need a correlation matrix, so we're going to scale it. Great. What if there's missing or discrete data? And essentially, it's the same. Okay. Essentially, it's the same trick. An EM model for this problem with missing or continuous data says instead of the covariance matrix, I'm going to take the expectation of the covariance matrix given the observed data. Okay, this is no longer maximum likelihood estimation exactly. It's an EM algorithm for it. Okay, so all I'll do, I'll replace the covariance the covariance matrix with the expected covariance matrix. And then I'm going to scale it to a diagonal. And then I'm going to repeat. Right. The reason that I need an iterative method for this is that the expectation of the covariance matrix depends on my estimate of the covariance matrix. Okay, but I can iterate this to convergence, and it works very well. It's essentially the same guarantees that EM generally does, which is weak. Okay, so every X step increases the likelihood. You do get a consistent estimate for the covariance matrix as long as the data is missing at random. And the E step is actually pretty hard. We use an approximate EM that's sort of based on 1D intervals.
Madeleine, can
Questions?
you
Yes.
estimate the function as well, or the function?
The function, the f's?
Yes.
Yes, so that's the easy part actually. What you do is you say, right, I'm just matching the distributions. Okay, so write down the CDF of each distribution, and the 99th percentile of the CDF for X has to match to the 99th percentile of the CDF for Z. Okay, and this actually gives you the whole thing.
Thanks.
Okay. Great. So how well does it work? I've been selling it pretty hard. Okay, so great. Okay, so first let's try it on synthetic data. So here's data that's actually generated from a Gaussian Copula model. It had better work better on this than anything else. Otherwise, we should all go home. I'm going to measure error in terms of the scaled mean absolute error. So this is how well am I approximating my missing value in the one norm compared to how well does the median approximate the missing value. Okay, so imputation by the median has SMAE of 1. Okay, so if it's less than 1, you're doing better than median imputation. You will see methods that do worse than median imputation. Okay. So first thing to check is that our EM method works at least as well as Hoff's previous MCMC method. And it converges very fast. It converges down to essentially the same asymptote as the MCMC method, but it works faster. The one exception is for binary data. So for binary data, actually you can get slightly better estimates by using the MCMC method than our approximate EM. Okay, but the more ordinal levels you have, the more the approximate EM stuff works as well. Okay, and it's a lot faster. Okay, compared to other models for missing value imputation, including Miss Forest, which is a non-parametric method, XPCA, which is a sort of, it's some low-rank nonlinear model, and Impute FMNP, we do better for any missing ratio on the synthetic data. Now let's look at some survey data. So here's one interesting survey data. This is the general social survey. You ask people a bunch of questions about how they feel about their life. Okay, 25% of the data is missing, and we masked another 10%. Okay, when you do this, you will find that the Copula EM method does a better job imputing any variable in this data set compared to all the other methods that we tried. So we were like pretty pleased when we saw this. This is the Hoff's method. And the reason it's not performing well is because it takes a really, really long time to run, and we stopped it after a reasonable amount of time. Okay, you can get some cool insights from this, right? So once you fit your Gaussian Copula model, you have correlations between every variable. And so in particular, you can ask for which correlations are large. So on this data set, you can conclude that people's happiness with their life depends most on people's happiness depends most on their satisfaction with their life, their level of health, their satisfaction with their finances, and their satisfaction with their job. Okay, notice that it doesn't depend directly on income, except through their satisfaction with their finances. Okay, that's kind of fun. Okay, so this was when I started getting really excited about this model, is when we tried it on MovieLens, because MovieLens is like the classic example where low rank matrix completion method, right, is like the right answer. Okay, and people will often argue that like data is low rank because low rank works on MovieLens. Okay, so let's take a subset of the MovieLens data. At first, we're going to take the 277 movies that have at least 1,000 ratings. Okay, so now we've made it skinny. Okay, there are only 207 columns, but we've got all the users who rate those movies, which is still most of the users. So 75% of this data is missing, and we're going to mask another 10%. Okay, when we do this, you will find that the Copula EM model is outperforming any other model on this data set, both in mean absolute error and in root mean squared error. And that's kind of cool, right? Because we didn't have to put in what kind of loss function we cared about before. Okay, it's doing well according to anything, because it's kind of trying to fit the whole distribution. Okay, the thing I find super interesting about this is that the best rank is very different for these different models. Okay, so for the low rank models, you don't get a consistent estimate of what the right rank is. So Several of the models are doing decently well, like XPCA is doing about the same as soft impute, is doing about the same as generalized low rank models, but they're getting really different ranks, okay? XPCA is using rank 6, generalized low rank models using rank 8. Soft impute is using the full rank that we allowed, which was 99. Okay, and then the Copula EM model is a full rank covariance matrix. Okay, so like, is the movie lens, right? Is the data really low rank? Like, it's well approximated by low rank, but like, you know, I don't think you should argue that, you know, any rank is fundamental here. Okay, great. Okay, so with that dissing low rank preface, let me introduce the low rank Gaussian copula. Okay, so what is the advantage of, okay, so the low rank Gaussian copula, all you say is that you're going to replace the correlation matrix with a low rank plus diagonal correlation matrix. Okay. Okay, the rest of the model is the same as the standard Gaussian copula. Okay, why would you do this? Okay, so you've got a low rank plus diagonal covariance matrix. This means that there aren't too many parameters in it. And it's also interesting, in this case, the Z follows the probabilistic PCA model. Okay, this model of low rank plus diagonal covariance is probabilistic PCA. Okay, so why would you do this? Has fewer parameters, so they're order P parameters, where P is the number of features. So it's pretty important to be able to estimate these models for large feature sets. So it means it's much faster to estimate. So for dense data, right, you have NP flops per iteration of the EM algorithm. For sparse data, the number of flops is proportional to the number of observations. Okay, it's not sensitive to the rank of the model you choose, unlike low rank models. So this doesn't overfit. You get better estimates as you increase the rank, but you know, just actually you often get pretty good estimates even for low rank. Okay, so this is just a computational trick. It's not like a real hyperparameter. Okay, just makes it more efficient. Okay, okay. So as usual, we first test on simulated data to see if it does well on data that's explicitly generated from our model, and then we try it out on real data. Okay, so here's our simulation setting. We've got a bunch of different settings. One is continuous, where the data is actually low rank. So we're going to generate low rank data like this, okay, as a low rank matrix plus Gaussian noise, sigma times E. We control the variance of the Gaussian with sigma. Okay, so our low rank data set is just going to be X is equal to Z. So X is actually low rank plus noise. The high rank data is X is equal to Z cubed. Okay, so we're going to do an entry-wise cube. And then we can also try it on ordinal and binary data, where we try different sort of variances, so different amounts of noise. Okay, so a low signal noise ratio and a high signal noise ratio. Okay, so let's look at the accuracy of this method compared to competing methods. And so we tried to find, you know, as many methods as we could, you know, cross-validate over all the hyperparameters, et cetera, et cetera. And so for the continuous data, we compared to soft impute, maximum margin matrix factorization with an L2 with the L2 loss, and monotonic matrix completion. Okay, so here, unsurprisingly, we found that when probabilistic PCA is the well-specified model, right, then it does better than anything else. Ours is close, right? It has extra parameters, so you end up overfitting a little. Okay, for the high rank data and for all of the ordinal and binary settings, we found that our method performs the best, though in the high signal to noise ratio, many other methods also do well. Actually, in the low signal to noise ratio, this is kind of interesting, right? Like using a model that's more flexible, right, works better when you have compared to the model that's less flexible, works better when you have high signal compared to when you have low signal. Okay. One of the coolest things about it is it gives you calibrated confidence intervals. Okay, so once you've estimated the model, you have, right, a complete, you know, you not only can impute the mean, you actually have a full distribution for every missing entry, full estimated distribution. And if you compute confidence intervals based on this, you find that they are calibrated. So we're trying to find the percentile confidence interval, and we find a confidence interval at 93%. That's pretty good. And the interval lengths are much lower compared to comparable methods. For the other ones, what we're doing is essentially you subsample, you bootstrap sample from the data, you fit the model multiple times, and then you use the sort of empirical distribution of the imputed values to model the distribution, take the 95% percentile interval for that. Okay, that's also a much slower procedure. Okay. Okay, if we use these confidence intervals to do something like figure out which entries we should be most confident in. Okay, so we can try using our confidence intervals, we can try using confidence intervals of competing methods. And what's interesting is that actually for some methods, like if you use maximum margin matrix factorization with an L2 loss, the entries that are predicted to be more confident actually give worse imputations. Okay, whereas ours actually, right, if you say you're more confident, then you are more confident. So like, right, this curve should be increasing. Okay, as you increase the fraction of entries of selected, right, the average error over those entries you're most confident in should be increasing. Okay, so we've got two implementations for this. One is in Python, one is in R. The Python also has an online streaming imputation, which is kind of fun. That's my phone, I'm sorry, please ignore it. Okay, so to conclude, so I've shown you this Gaussian Copula model for data imputation. The things I like about it are that it has no hyperparameters except for computational speed. It outperforms a lot of fancier non-parametric methods. It gives you confidence intervals for the imputations. And it's fast and easy to estimate for moderate numbers of features. And using a low rank covariance, you can make it scale to essentially as large data sets as anything else. So thank you.
Great. Thank you so much for a very interesting talk. We have a few questions. I think we have some queued questions from Prathipa. I don't know if you want to ask him directly.
Yeah, sure.
Okay.
The first question was about whether when we do the matching of quantile, do we use distribution function or density function? And if it is a distribution function, do we use continuity correction for discrete data or Boolean data?
So I guess for this, I should go back to the actual mathematical formula, which I essentially skipped. The answer is that we use the cumulative distribution function. Where am I? Yeah, estimating the marginals. So here, and we do the continuity correction. This guy.
Oh, with the continuity correction. Okay.
Yeah.
Thank you.
Yeah. Otherwise, you end up with infinities. So we don't like infinities. Yeah.
And the other question is about the metric. I want to know whether we use different metric to evaluate the imputation error for ordinal and continuous variables.
So in all of our experiments, we just use the scale mean absolute error for all of those.
Okay.
But you can use any metric that you like. I guess what's nice about the Gaussian Copula method is that you don't have to put in the metric in advance to tell it what imputations to make, right? It's just trying to learn the distribution, right? As opposed to many of the low rank matrix completion models that require a loss function, you have to say first what you care about before you can fit the model.
Okay, thank you. And the last question is, do we know whether we need all the variables, because it is a survey sampling survey table, but I'm still wondering whether do we need to consider all the variables are important for the downstream analysis? Do we need to impute
yes.
everything?
Yeah, so this is right. So if you're fitting a low rank model and you include a bunch of variables that are unimportant, not correlated with the rest of everything, but you're trying to fit it all with a low rank model, then they're going to end up pulling you away, right? You're going to end up sort of devoting some of your precious degrees of freedom to fitting them. With the Gaussian Copula model, if you're adding in variables that have nothing to do with anything, then you're going to, well, I mean, they might add some noise, right? They will still in general add noise, but if you allow a full rank covariance, like, with enough data, you should find that these variables are not correlated with anything else, and you can actually represent that.
Okay, so it means
we haven't done these experiments. That's actually an interesting point. But like I believe that adding in spurious columns that don't really matter is going to affect this model less badly than a standard low rank model.
Thank you.
Rene, I think you also had questions.
Yes, thank you, Madeleine, for a great talk. It's great to see you again.
Good seeing you.
I was trying to understand if you could clarify a little bit, what are the primary differences with the work on probabilistic PCA with missing entries?
Essentially,
and in particular, when thinking about it, my sense was that the model is generally very similar. They also had the EM algorithm for doing the imputation.
Yeah.
And the primary distinction is these assumptions that for the marginals, that they're the entry-wise monotonicity assumption. And so I was trying to understand why that makes a difference. What is the intuition behind it? And if you had a back-to-back comparison with probabilistic PCA with missing entries with the same EM algorithm.
Yep, so I've got that actually. That was this comparison. So what's the reason? So right, the difference between the low rank Gaussian Copula model and probabilistic PCA is the fact that you're saying you're allowing yourself to measure the data with the nonlinear ruler. Okay, so probabilistic PCA says the data that I have observed really does follow this, right? It's Gaussian with a low rank covariance matrix, low rank plus diagonal. Okay. My model says, no, the data is generated by mapping that through some nonlinear functions. Okay, so the more weird these nonlinear functions are, the more important it's going to be to actually estimate them. And this is what you see. This is what you see in these experiments. Okay, so if the probabilistic PCA model is the correctly specified model, I haven't mapped it through a nonlinear function, then it does better, right? If I have mapped it through a nonlinear function, right, then the low rank Gaussian Copula does matter. So.
But what is I guess I'm trying to understand.
So as an example, for income, let's imagine that one of our variables is income, okay? Income, absolute, right? So in probabilistic PCA, the marginal distribution of any value, right, of any feature should be Gaussian, okay? Income absolutely does not have a Gaussian distribution, okay? And fitting it with a model that assumes it has a Gaussian distribution is absurd.
Great.
Yeah.
Thank you. That's great.
Yeah.
Any other questions or comments?
I think Stephen had a question.
Yeah, actually, just sort of one more point on that is oftentimes you'll pre-process the data in order to make it have a more Gaussian distribution. For example, in finance, you'll take log returns instead of returns. So we've run this on some financial data, and what's interesting is that the other methods really care whether you did that pre-processing, and our method is the same whether or not you do the pre-processing or not. So if you have special knowledge of what it takes to make your data Gaussian, then go ahead, use it, right? But if you don't, then this model doesn't care.
Steven, I think you had a question.
Yes, thanks for the nice talk, Madeleine. Yeah, I was wondering about an intermediate or hybrid problem, which is as follows. I'm given a matrix, and I suspect that there's a univariate monotone function that if I apply it to all the entries, I'll get a low rank matrix. But I don't know what it is. Is that a problem that's studied, and is there a solution to it?
I'm tempted to say that this is the solution, but it's not quite, right? Because this also has this Gaussian assumption, right? So I don't know the solution to that. I mean, this is very related to Laura's work. That was essentially the problem that Laura and Becca and Ravi Ganti were studying. But I don't think that there are known really good numerical methods for that problem.
Renee, your hand's still up. Is it another question or just from before?
No, sorry, I forgot to remove it.
Okay, no worries. Any other questions or comments? Okay, so this concludes, I guess, our session, our morning session, and I look forward to seeing you at 1 p.m. Eastern time.
Okay.
See you soon. Thank you to all the speakers.
See you in half an hour.
So Laura, I hope I correctly represented your work.
Yeah, great. And I learned a lot about yours. Thank you so much for the presentation. It was really
Can I ask you offline a question?
Sure.
You mentioned finance, and in
Sorry, can you say
2008.
who this is?
Sorry?
Can you say who's asking the question? This is Itamar?
Yeah, Itamar, yeah. You mentioned finance, and Copula was underlying the problem of 2008. And I think the person who pursued it was David Lee, if I'm not mistaken.
Mm-hmm.
Now, the question is now twofold. Your study is wonderful, and you discussed accuracy and everything, no problem. However, did you look at the issues around the copula in your context? That's question number one. Question number two is even deeper curiosity. Could you use the imputation method that you established so well to, in retrospect, could one use your method to avoid the crisis?
Absolutely not. So essentially, what's the problem with the crisis? What's the problem with the crisis? So here's the problem. So fundamentally, the problem is that financial assets get more correlated as you move to extreme values. Okay, so when everything goes south together at the same time. Okay, Gaussians don't do this. So if you're using, the Gaussian Copula model, it can deal with heavy tail distributions a little bit better because it sort of reins them in and transforms them to Gaussian and treats them in that way. But the correlations are still Gaussian. And so according to this model, it's going to be very unlikely for several variables to have a large excursion to the right or the left at the same time. And in finance, that's a thing that absolutely happens and is very important. Okay, so some people try to fix this by moving to different copula models, like they'll use a student T copula model, which has fatter tails.
So this is
I don't have
Gaussian.
strong beliefs. I mean, that's better. It's much more difficult computationally, which is why we didn't handle it. But it's slightly better from a modeling perspective. But I still don't have any real beliefs about whether that handles the problems. I think fundamentally the problem is that in finance, extreme events are essentially the most important part of finance. And any model that tries to learn from data is going to fail for those extreme events because there aren't a lot of them. So it's like a fundamental problem with learning from data for finance. Like you'll do well most of the time, but when the music stops, you're in trouble. Like that's just fundamental to any algorithmic approach that I know of for financial data.
Okay, interesting. Is there something like non-Gaussian copula?
Yes, the student T copula is the one that's been the most studied after the Gaussian.
So which one David Lee used?
Gaussian.
Oh.
The student key copula is much harder to compute with. Like, yeah, computing the parameters of that model is like not easy.
I don't get, how do you call it? Student key?
Student T, like the, you know, the student T test
Oh, the
from
high,
statistics.
the high, that Greek letter, student key.
No, student T. I'll write it in the chat, student T.
Okay.
But it helps, but it's not a solution.